In this video, we're going to look at how to evaluate limits with using algebra, so we will not be able to see the graphs on these types of problems. So the basic method for solving a limit is to just use direct substitution, and that means just plug it in. Most functions are polynomials, they're normal, so the value will be the limit. Here, this just kind of writes them out. If we use direct substitution, we're going to plug in C here, and it's equal to C. There are different properties. I'm not going to explain every property. You can come back and review them later if you want to. The important ones I will highlight, though. Okay, so properties here, again, we just use direct substitution. There's no special rules. If we're adding, we find the limit of each piece and add our answers. If we're multiplying, same deal. We multiply our answers. The only kind of hang up and the only thing that's going to require more work is if we do have a fraction and if the limit of the bottom gives us 0. Then we may need to do some more work. So, examples. Remember, function notation says the limit of f of x. So this is f of x. This is the function. It's always 5. It's 5 no matter what. No matter what we're approaching, this guy's equal to 5. The other way to look at it is there is nowhere to plug this in, so it's just going to be 5. A more common type of problem is example 2. Again, we want to see, can we just plug this in, right? And this is a polynomial. Polynomials are going to be continuous everywhere, so at 1, we're going to be approaching the same value as the y value. So we just try to plug it in. So this is going to be 2 times 1 to the third plus 4, or 2 plus 4, which is 6. Again, there's a lot of theorems on here. I'm not going to talk about every single one. The main problem is when this guy here equals 0. Then we need to do more work. If there's a radical involved, we still just use direct substitution and plug that in. A composite function is a little bit more complicated. We actually just find the limit of the inner function and then we plug it in. We're not going to actually practice that in this course. So example 3, again, when you see a limit, try direct substitution. Sometimes it will work. So if I plug this in, I get that. There's nothing wrong with the denominator. It's not equal to 0, so I simplify, and that is my answer. If trig is involved, again, direct substitution works because trig functions are continuous. So I can just plug it in, and whatever the y value is my limit. Okay? Here we have a really good visual of what happens when we factor. When we are given a rational function and we factor and divide, the answer that we get results in exactly the same graph. The only difference is in the original, if we had a point that was undefined in the denominator, that creates a hole, whereas once we simplify, it creates a defined point. That is the only difference. So this is what we're doing when we are factoring and canceling. We're creating something that looks almost the same, it's just we can use the result to find the limit. Okay? If I were to look at this original graph to find the limit, to find the point here, I can't find it because it doesn't exist. But if I use the new function, it does exist, and I'm able to see easily that it's 3. So, some examples. Again, example 5. Here, we just try direct substitution. The sign of pi over 2 means we need to look at the unit circle. Pi over 2 is right here on the axis at 0, 1. The sign is 1. Example 6, again, we try direct substitution. If we do that, we end up getting 0 over 0. This is called indeterminate form, which means we cannot determine the value. We must do more work. This tells us nothing. Okay? So, we try to factor. The numerator is a difference of perfect squares. So we can find the limit of the resulting simplified version. So all we've done is factor. When it's written as a multiplication problem, we can then divide factors. So I'm going to divide. And if I can find the limit of the resulting equation, That's going to be the limit of the original. So, direct substitution, 1 plus 1 is 2. So, just remember in the picture that we saw on the last slide, the graph of this is exactly the same as the graph of that, except there's a hole when x equals 1, because that's what makes the denominator equal to 0. Okay, 2 special trig limits. These you kind of do need to memorize. Those are the only 2 that you have to memorize from this section. The way I remember them, this is not mathematical, this just helps me remember, is that in this one, I can kind of look at this as x divided by x, which is 1. Over here, I can do x divided by x, and then I can do 1 minus 1 to get 0. But again, that's not mathematical, that's just how I remember which is which. Okay, so here's kind of how we find limits. We try direct substitution first. If that doesn't work, we try to factor and simplify. Then we still go back to direct substitution. If we have a graph, great, but we usually don't want to make a graph for these problems. Indeterminate form, in means we can't. So we cannot determine if this is what we get. We must do more work. So a couple more examples. Example 7 here, again, we just plug this in. So we get pi times the cosine of pi. There's not a problem here, so we just evaluate. The cosine of pi is going to be way over here. My cosine is equal to -1. So I end up with pi times -1 or negative pi. Okay, number 2, when we plug this in, we do end up getting indeterminate form. Again, that doesn't tell us anything, so we must keep going. When I see tangent, I really like to work with sine and cosine. Plus, our 2 special limits use sine and cosine. So we want to take this and translate it into sine and cosine. When we do that, tangent's equal to sine divided by cosine. So I'm just keeping my fraction. Sine's on top, cosine's on the bottom, and this x is on the bottom, so he stays on the bottom. Now I can kind of split this up in a different way. I can say, well, I want to pair these together because then it matches this. So cosine is still on the bottom, and sine and x are just going to be kind of separate now. And so the limit of this piece is 1. And now this is what I still need to evaluate. So it's 1 over the cosine of 0. And the reason I put 0 in there is because I'm using direct substitution. And the cosine is 0. 0 radians is here. The cosine will equal 1. So we get a final limit of 1.